All right, in this video, we're going to take a look at performing vertical stretches and compressions of functions. So we're going to use a function, parent function that we did not look at in the previous video, and we will spend time later on in the course dealing with this function. But for f of x equals sine of x, examine the effects of g of x equals a times the sine of x, where a is greater than 1 and also where a is between 0 and 1. So let's go to our graph, and again, our parent function's in red. Right now we have 1 times sine of x, which doesn't change anything when you multiply something by 1. So here's what our sine function looks like. It's wavy, kind of like a slinky. So let's take a look at what happens as we increase the value of this a, starting at 1. And let's see what happens as we increase a. So as we can see, our graph is getting taller. In fact, it's getting taller above the x-axis, and it's also getting taller below the x-axis. So it looks like it's being pulled away from the x-axis, both upwards and downwards as well. So it would seem as if our graph is stretching here. So, okay, it would appear if we multiply by a number bigger than 1, it's going to stretch the graph away from the x-axis in both directions. Notice where it crosses the x-axis, though, no matter what, that's not going to change at all. So it's like we put in some thumbtacks where it hits the x-axis, and those don't change, but everything else we kind of pull upwards and away from the x-axis, both upwards and downwards, and it stretches it out from a vertical perspective, so it gets warped. All right, now let's look at what happens if we multiply between a is 0 and a is 1. So here's 1, and as we now bring it down closer to 0, notice the blue graph is getting closer to the x-axis. So it might be beneficial to zoom in here. And the closer it's getting to 0, the closer our graph is getting to the x-axis. Notice again where it hits the x-axis, nothing's happening there. But this, don't worry about this pi over 2, this had a height of 1 from the x-axis. Now it has a height of 0.497. So what's happening when we multiply our function by a number between 0 and 1 is it's pressing it downward towards the x-axis. So it's compressing it closer to the x-axis. So compressing gets closer. So a vertical stretch, which we saw when a was greater than 1, or vertical compression, which we saw when a was between 0 and 1, is obtained by either vertically pulling on or pressing on the graph. And a vertical stretch, as we saw with values of a that were greater than 1, is going to pull the points away from the x-axis, with the exception for the x-intercepts. While vertical compression, on the other hand, as we just got done seeing, pushes or presses the points towards the x-axis. So stretch is pulling them further away. Compression is pushing them towards, closer to the x-axis. So algebraically, we get those vertical stretches and compressions by multiplying our function by a positive number, either between 0 and 1 or greater than 1. Remember, if we multiply by 1, nothing changes. So multiply by 0 just wipes everything out. So the value of a is going to determine whether or not we have a vertical stretch or a vertical compression. So if our value of a is greater than 1, like it was at the start when we first looked at the effects of what happens, that's a vertical stretch, and it's a vertical stretch by a factor of whatever that value of a is. And in this case, with a vertical stretch, the factor tells you how many times further away from the x-axis your y coordinates are. So for instance, we'll go back to a is between 1 and 10 here. Don't worry about this pi over 2 point, but this pi over 2 x coordinate is 1 space away from the x-axis. If I change this now to, let's say, 2.5 times the sine of x, again, I started off 1 unit away, but now if I multiply my function by 2.5, now at that same value of x, I'm now 2.5 spaces away from the x-axis. So my point now is 2.5 times farther away from the x-axis than it used to be for those vertical stretches. A vertical compression, when your value of a is between 0 and 1, the factor is the reciprocal. The reason for that is because compression is going to measure how much closer to the x-axis we are now versus what we were originally. So let's take an easy one like a half. A half is between 0 and 1. So if we take a look at, we'll go between 0 and 1 again. And I know that a half is between 0 and 1. So now our original graph is in red. It's 1 unit away. When x is pi over 2, it's 1 of a y value of 1. Now let's look at this 1/2 sine of x. At the same value of x, our y coordinate is now half of what it used to be. And in terms of factor and compression, this point here on the blue graph is now twice as close to the x-axis as the original point was. So this is only a half a space away. This is a whole space away. So this point is twice as close on the blue graph as the point on the red graph. So compression is a matter of closeness. Stretching is a matter of further away. So vertical stretches and compressions, as we saw, are going to multiply the y coordinates of our function by whatever the value of a is. And again, the factor will always be expressed as a value greater than 1. If it's already greater than 1, that's the factor. But if we have something like a half, we take the reciprocal of a half, which is 2. So 2 is greater than 1. And that's because now the points are twice as close with compression, twice as close to the x-axis as they were originally. All right, example 3, list the parent function and indicate if it's a vertical stretch or compression, then list the factor. So we have g of x equals 2 times the square root of x. Well, our parent function, as we saw from the previous video, would be the square root of x. And then we're multiplying it by 2, which is a number bigger than 1. So it's a vertical stretch by a factor of 2. And if we want to see that, we can just go ahead and type in the square root of x. And we can do 2 times the square root of x. And notice how with this one, it pulls the graph vertically away from the x-axis. So my original point here at x equals 2 was 1.414. Now with x equals 2, I'm at 2.828, which is twice the amount of 1.414. So again, our points now are twice as far away from the x-axis as they used to be. Part B, we have 3.5 times the cube root of x. So our parent function is the cube root of x. We're multiplying it by 3.5, which is bigger than 1. So it's a vertical stretch by a factor of 3.5. So now all of our points are 3.5 times further away from the x-axis than they used to be. Part C, g of x equals 1/3 x squared. Well, x squared is our parent function, and we're multiplying it by 1/3, which is between 0 and 1. So it's a vertical compression, and we take the reciprocal of a to get the factor for vertical compression. So the reciprocal of 1/3 is 3, because each of the points now are 3 times closer to the x-axis than they used to be. So again, if we want to see that, we can make x squared really easily, and then we can make this 1/3 x squared. And now what happened is it took our red graph and pressed it downward towards the x-axis. So it did get the graph to look a little wider, but if we take, for instance, when x equals 2, on the original graph we have 4. Here, when x equals 2, we have about 1.33. We have 1 1/3. So this point here is 3 times closer to the x-axis than this point with the same x value on our parent function. So again, compression is closeness to the x-axis. All right, part D, we have g of x equals 2/5 times the absolute value of x. Parent function, again, is the absolute value of x. 2/5 is between 0 and 1, so kind of like that last example, it's going to press downward on it towards the x-axis. It's a vertical compression by a factor of, the reciprocal of 2/5 is 5/2. So vertical compression by a factor of 5/2, or 2.5. So if we multiply our function by 2/5, that means that all of our y coordinates are now going to be 2.5 times closer to the x-axis than they used to be. All right, so that about does it for this video. Thanks for watching. I'll